This is the Easy Guide to Medical Statistics Part 2. I'm Dr. Hutton. I'm an OBGYN, so some of the samples and examples will be OB related, but they can be expanded to understand any medical literature. You will learn about prevalence and incidence, odd ratios, and risk ratios. So prevalence and incidence. Prevalence is the total number of cases at a given time. So it is all the cases at one specific time. The incidence is the number of new cases or diagnoses over a certain time period. So this data is loosely derived from HIV data. So in the 80s, 800 new cases were diagnosed. So the incidence in the 80s is 800,000. We lost 50,000 diagnoses to either death or cure, resulting in a net of 750,000 cases at the end of the 80s. In the 90s, 200,000 more people are diagnosed, so the incidence in the 90s is 200,000. We lose another 20,000, resulting in a net of 180,000 new cases in the 90s. In the 2000s, 200,000 people are diagnosed, so again, our incidence in the 2000s is 200,000. We lose 10,000 cases for a net of 190,000 cases. So then if we want to know what the prevalence is at the start of 2010, it is 1,120,000 cases. And we get this by adding up all of these. So I'm going to switch back to OB for a minute and preeclampsia. So in the United States, the incidence of preeclampsia is 10% overall, but 5% in women without any risks. The incidence from 20 to 32 weeks is 3%, or 3% of women who are pregnant in the US will develop preeclampsia from 20 to 32 weeks. After 32 weeks, another 7% will develop preeclampsia, for a total of 10%. So the prevalence at the end of all pregnancy is 10%. But in pregnancy, as pregnancy is a definite period of time, you could also use incidence. So this is how we get the incidence of preeclampsia. So in pregnancy, there's no wrong answer. So more on risk factors. So this list is from Medscape, and these are risk factors of preeclampsia. And this list gives us the odds ratios. And you'll see that the odds ratios vary, and in fact they do carry some weight, such that someone with chronic hypertension has a much more significant chance of developing preeclampsia than someone who's just having her first baby. But what does this mean? So what is an odds ratio? And if the prevalence of preeclampsia is 5% in the general low-risk US population, and chronic hypertension has an odds ratio of 10, does a person with chronic hypertension have a 50% chance of preeclampsia? It turns out about 35% of women in the USA with chronic hypertension will get preeclampsia. So it appears that an odds ratio exaggerates the risk. So what is the difference between an odds ratio and a risk ratio? The risk ratio to me is the real risk. A risk ratio of 5 means you have a 5-fold risk, but this is not true with an odds ratio. So how do you choose which one to use? Odds ratio versus risk ratio. You can only use a risk ratio if you sample the entire population at risk, or if you sample enough people, participants, to have a good estimate of the risk of the entire population. Otherwise, you use an odds ratio. So this is as simple as I can make it here. You only use the risk ratio if you sample the entire population or enough of the population to feel that you have an estimate of the risk of the entire population. So in some ways, the odds ratio is the default that you use, and it's much more common. It's often used in smaller populations with rare, less common conditions and many exclusions. It's often used in retrospective studies, not always, but often. It exaggerates the value, as we saw. The denominator is those in each group without the disease. The relative risk is used in large population studies, often multi-center studies. They are often prospective studies, again, not always, but often. And the denominator is the whole population at risk. So let's look a little bit more at this. Say we sample 100 women as they walk in the door at 2 different clinics. Clinic 1 is a high-risk OB clinic where 53 of 100 women walking through the door have chronic hypertension. And Clinic 2 is a low-risk OB clinic where 10 out of 100 women have chronic hypertension as they walk in the door. So what's the odds ratio and what's the risk ratio for having chronic hypertension at the high-risk clinic versus the low-risk clinic? The odds ratio. 53 women in the high-risk clinic have chronic hypertension, over 47 do not. And you divide this by the low-risk clinic where 10 women have chronic hypertension and 90 do not. This gives us an odds ratio of 10.1. Sometimes you'll see it given this way, and due to properties of mathematics, you can, either way, you're going to get the same answer. So in this version, 53 women in the high-risk clinic have chronic hypertension, whereas 10 in the low-risk clinic have chronic hypertension. And we divide this by 47 in the high-risk clinic do not have chronic hypertension versus 90 in the low-risk clinic. For the relative risk, you use the whole population. So 53 women have chronic hypertension out of 100 over 10 women in the low-risk clinic over 100 gives you 5.3. So you can see the denominator here is different from here. So now we're going to use an online calculator to demonstrate this. This again is Vassar stats, the 2x2 contingency table, and we're going to use this now looking at risk ratios and odd ratios. So in our 2 clinics, our first clinic, the high-risk clinic, 53 women have chronic hypertension and 47 women do not. And 10 women in the low-risk clinic have chronic hypertension and 90 women do not. So then we hit calculate, and so right here, it gives us the odds ratio and the risk ratio. We don't need to put anything in differently. The odds ratio is 10.1 and the risk ratio is 5.3. Note that 5.3, when you use 100, it's very easy to look at. If you were to divide 10 into 53, you would get 5.3. It is the true risk or multiplication of the risk here. Next, we're going to get into confidence intervals of the risk ratio and the odds ratio, which it gives here. And as well, we're going to talk a little bit about what the p-value means. Okay, so what is a 95th percentile confidence interval? If you look up the definition of this, there are multiple different ways to look at it, but this is one that I like. The 95th percentile confidence interval is a range of values. You can be 95% confidence, contains the true value, whatever that is, the mean, the odds ratio, the relative risk of the population. So here we have our typical bell-shaped normal distribution, and this is our odds ratio of 10.1. And the video before gives us the confidence interval of 4.7 to 21.8. And so this is where we're 95% certain our odds ratio lies. 1 is over here. The p-value answers, does the odds ratio equal 1? If it is less than 0.05, it does not. And 1 would be over here if this is 4 and 10 and 21. And you can see it's very much outside of where our confidence interval is. So generally, you're not going to see a bell-shaped curve. You're just going to see a line, and where they mark their odds ratio, mean, risk ratio is. And they'll often mark 1. And the reason is, if your 95th percentile confidence interval crosses 1, then this is not statistically significant. So a few knowledge tests. A study lists many exclusions and has 2 population arms of about 100 participants each. It compares the outcome between 2 populations with a relative risk. What do you think? In general, they probably should have used an odds ratio here. If you have many exclusions and only 100 participants in each group, probably an odds ratio. However, sometimes a relative risk can be appropriate, especially if you're doing a pilot study that you want to then use for power analysis. Another knowledge test. A study shows that women who drink 2 to 3 glasses of wine a day have an odds ratio of 1.2 of breast cancer. The news reporter quotes that the study showed that drinking 2 to 3 glasses of wine causes a 20% increase in the rate of breast cancer. Is this correct? So technically, relative risk is when you can say 20% increase. However, I can tell you that this is often done with odds ratios. And let's look at this a little bit because it's actually not that far off. So this graph has risk ratio and odds ratio, and these are different incidences within a population. So you'll see right around 1, they converge. So something that's 1.2, an odds ratio, is typically not going to be that far off from a risk ratio. But note that as you get higher up, the odds ratios really exaggerate. And so if you were to have an odds ratio of 6, that really might only equate with a risk ratio of about 1.6. So you need to be careful as you get away from 1. I'm going to talk a little bit about the meta-analysis. A meta-analysis compiles the data from many studies trying to answer the same question. For instance, is alcohol consumption associated with an increased risk of breast cancer in women? A few words to the wise. Tread carefully before attempting a meta-analysis. Read how-to articles in respected journals, register your meta-analysis, and keep very detailed records on all your searches. So this is a meta-analysis of alcohol consumption and breast cancer risk. And these authors compiled some 22 studies, all trying to answer this question. So a few things to note. This is one, and you'll see that many of these studies do not reach statistical significance, and some of them do. And this one over here, although it does not reach statistical significance, it actually shows a possible protective effect. So with this, I would say that this is why a lot of statisticians, if an odds ratio or relative risk is less than 3, they don't give it much merit until you put together something like a meta-analysis, because any of these taken alone gives you a risk, but they are kind of all over the place. A few other things to note. Some of these have very large confidence intervals, and some of them have very short confidence intervals. In general, a longer confidence interval is a study population that is smaller, and a smaller confidence interval is usually a larger population study. And so these, with the small confidence intervals, carry a lot of weight, and these with the big confidence intervals are usually smaller populations and they carry less weight. And so then you put these all together, and it turns out that the relative risk, which is what we're looking at here, it all needs to be the same, is about 1.17 from all of these studies. And you get a very narrow confidence interval when you put them all together. Of note, there are some meta-analysis online calculators that I need to evaluate, and once I do that, I'll potentially put together a video.